Have you ever wondered how machines learn to classify data? How they distinguish a cat from a dog or an apple from an orange? Well, one answer to this fascinating question is a machine learning algorithm known as Learning Vector Quantization, or LVQ. This supervised learning method is a stalwart in the field used in a multitude of applications, from speech recognition and image processing to natural language processing. So let's dive into the architecture and training algorithm of LVQ. At its core, LVQ has a straightforward architecture comprised of an input layer and an output layer. Each feature in your input data is represented by a neuron in the input layer, while each class in your classification problem gets a neuron in the output layer. These neurons are interconnected through weighted connections, the values of which are learned during the training process. So, how does the training process work? First, we initialize the prototype vectors. This can be done randomly or with some prior knowledge about the data. For instance, if we are training an LVQ classifier to distinguish between cats and dogs, the prototype vectors could be initialized to be images of a cat and a dog. With prototype vectors in place, the training process begins. For each training data point, the LVQ classifier finds the winning prototype vector, the one closest to the training data point. This winning vector is then updated in the direction of the training data point. The extent of this update is controlled by a learning rate parameter, which determines how quickly the prototype vectors evolve. This training process continues until the prototype vectors reach a stable state. That is, they are no longer moving significantly. At this point, the LVQ classifier is ready for action. To classify a new data point, the classifier finds the winning prototype vector and assigns the new data point to the class of this winning vector. Let's take an example. Imagine we're training an LVQ classifier to differentiate between cats and dogs. We start with prototype vectors initialized as images of a cat and a dog. Then, for each labeled image in the training set, the classifier finds the winning prototype vector and updates it in the direction of the image. If the image is a cat, the cat prototype vector is updated. If it's a dog, the dog prototype vector gets updated. The training continues until the prototype vectors stabilize. Once they've converged, the LVQ classifier can be used to classify new images of cats and dogs. In conclusion, the Learning Vector Quantization training algorithm is a simple yet robust method for training classification models. It's not only easy to implement, but also versatile enough to be applied to a wide array of problems. However, bear in mind that LVQ can be sensitive to the initial setup of prototype vectors and may be slow to converge for larger data sets. So the next time you see a machine flawlessly classifying data, remember the clever and powerful LVQ algorithm might be at work.
In the world of machine learning, Learning Vector Quantization, or LVQ, holds a position of significant importance. This powerful classification algorithm is a master of simplicity and efficiency, often acting as the unsung hero in a diverse range of applications. Delving into the advantages of LVQ, it shines in its ability to handle complex and non-linear problems. This robust algorithm is a powerhouse when it comes to dealing with multidimensional data. This makes LVQ a reliable partner in crime for tasks such as speech recognition, image processing, natural language processing, medical diagnoses, fraud detection, and even text classification. Moreover, LVQ's ability to create prototypes for each class in the dataset allows for an intuitive understanding of the data. These prototypes essentially act as representatives of the classes, providing a clear visualization of the structure and nature of the data. However, every rose has its thorns. One of the disadvantages of LVQ is the sensitivity to the initialization of the prototype vectors. The success of this algorithm heavily relies on the correct initialization of these vectors. A misstep in this process can lead to the algorithm struggling to learn the underlying structure of the data. Another disadvantage is the time it takes for LVQ to converge, especially with large datasets. The process of the prototype vectors reaching a stable state can be a slow one, often requiring patience and computational power. Despite these challenges, LVQ stands tall as an algorithm of choice for many classification problems. It's a testament to the balance of machine learning, the interplay of strengths and weaknesses. To summarize, LVQ in its simplicity and power is a versatile player in the field of machine learning. It excels in handling complex multidimensional data and offers a clear understanding of the data structure through its use of prototypes. However, it does come with its share of challenges such as sensitivity to the initialization of prototypes and a potentially slow convergence rate. Yet these challenges do not overshadow the benefits LVQ brings to the table, making it a dependable choice for various applications. In the vast landscape of machine learning, learning vector quantization continues to hold its ground, proving that sometimes simplicity and efficiency can indeed lead to powerful results.